Welcome back to another lecture from Organic Chemistry, a survey of organic chemistry. In this chapter, which is going to be a new chapter, chapter 2, we'll be covering acid and bases. And we're going to try to use a term like pKa and to figure whether a chemical reaction is going to move on or not. Okay, first we need to know what's the meaning of acid or base based on definition of Bronsted-Lowry. Definition: acid is a compound that's going to donate a proton or H plus, and we call this one hydrogen ion. Or if it's accepting H plus, we're going to call it base. Okay, so in this example, we have HCl reacting with water and is giving us chloride ion plus hydronium ion. And this reaction should be 100% conversion, not double errors. Okay, and I will talk about it very soon. Okay, so what do we have here? We have HCl reacting with water, and the reaction is going to go through 100% conversion, and I'm going to write it with a single arrow. That means whatever I start with, it will be gone. Okay, now let's highlight the number of H that attach to a chloride. We have one of them, and other side, I don't see any H attached to chloride. So clearly HCl donated one H plus to water. So we're going to say minus H plus, and this is going to be the acid, and wherever H plus went, that side is going to be the base. So this is going to be the base. Now let's find the leftover of HCl. The leftover of HCl is the Cl. This is going to be the conjugate base. I started with acid. Leftover after giving H plus, it will be the conjugate base. How about the water? We could call it in base because accepted H plus. Now, if we track number of hydrogen that attached to it, we have 2 here. Now we have 3 of them. So clearly we got 1. And so I'm going to say we started with 2, we ended with 3. That's a base, and other side it will be the conjugate acid. Okay, if you call it acid, it must have H plus. Okay, it must have H plus. Otherwise, it's, or at least it must have H attached to it. Then you can call it conjugate acid. If there is no H attached to it, that's not going to be an acid, because acid should be able to donate H plus. Okay, another one. I have 3 hydrogens here. Okay, ended with 4. Okay, so clearly we accepted 1 H. And because we accepted 1 H, we took 1 H from water. This is going to be the base. And water, it will be the acid. Okay, let's look to NH3. Okay, we got NH4 other side, so I'm going to call it conjugate acid. As you see, now we have H plus that we can actually give it to somewhere, and that's the reason we call it conjugate acid. Water had 2 hydrogens. Now it has only 1 and is missing 1 H, and this one we're going to call it conjugate base. Okay, another example. Okay, we have an ion. It has negative charge. This ion is looking for H plus to be neutral, so it's going to take that H plus and it will turn to organic chemistry. We call this one tertiary butoxide. The ion tertiary butoxide reacting with water is giving us alcohol plus OH. Okay, so this is going to be the base. How do I know is the base? Forgive me, I should actually draw the arrow other side. And because it's accepting H plus, okay, accepting H plus from water. So this one is accepting H plus, so minus H plus from water. And that's going to be the acid, or tertiary butoxide, it will be the base. Okay, if this one is the base, okay, after gaining H plus, it will turn to conjugate acid. And yes, it does have H plus there. Okay, and OH, it will be the conjugate base. Okay, cool. I'm sorry. Now, we have a base reacting with HA and it's turning into BH plus A9. The question is like, what's the meaning of those errors and how do we break the chemical bonds? Okay, how base is going to break that HA bond? Okay, the error that you see, okay, the error is showing you that base is giving 2 electrons to HA to take the H plus from it. And A is going to take those 2 electrons. But the question is, hydrogen, it has only 1 orbital, okay? And is already used to make a sigma bond with A. So where do you want to put the electrons of the base? Okay, let's draw a molecular diagram of HA. So we have HA, okay? This is HA. Let's say we have H reacting with okay, and then A interacting with H, we get 1 bonding orbital. Let's call the bonding orbital sigma of HA or AH, doesn't matter. Okay, and we're going to put 2 electrons in it, up, down. So we got the sigma, and this is going to be a bonding orbital. Okay. Now, how about the second orbital? The second orbital, it will be an anti-bonding orbital. We call it sigma star, okay, of HA. This one, it will be anti-bonding orbital. Okay, now let's define the bond order. What was the bond order? Bond order is equal to bonding electrons, bonding. Okay, so I'm going to say bonding electrons minus anti-bonding electrons, and you take this and you divide it by 2. Okay, why 2? Because for each bond, we need to have 2 electrons. So what's going to be the bond order? Bond order, it will be this. Okay, I'm going to write it here. Bond order, it will be 2 minus 0 divided by 2. That's going to be 1. What does it mean? It means H will attach to A through a single bond. Okay, through a single bond. Now, we got the molecular diagram of HA. Okay, let's show interaction of B with HA. So we have A attached to H, and then base is coming with 2 electrons. The base, it has a lone pair, that's -1. Base is going to give 2 electrons to the H. But where do you want to put them? Base is going to put 2 electrons inside the anti-bonding orbital or the sigma star of HA. And if you did, this is going to happen. Okay, you get 2 electrons inside that orbital. Now calculate the bond order. The bond order for HA. Bond order for HA. Okay, it will be 2 minus 2 divided by 2. It will be 0. What does it mean? It means we broke the bond. The AH bond is gone. So this bond is gone. Now we got new interaction, and an interaction between B and H. And I'm going to show it by solid line between H and B. Okay, remember, we had 2 electrons. Attach 2 electrons between H and A. Those 2 electrons will be taken by A. So we get this. Other side, we're going to get A with a lone pair or -1 plus HB. Okay, so the base is going to put the electrons inside anti-bonding orbital of the base is going to put the electrons inside anti-bonding orbitals of the HA or the acid. So then you can actually break the bond and take H from the acid. Okay. Again, here it's showing us that our OH is donating 2 electrons or a lone pair and is putting electron inside sigma star orbital of H, okay? And it will take H from the system. So if you take that H, whatever left, it will be, okay, this one, it will be the conjugate base, okay? And so that one, it will be the conjugate base. And OH, after accepting H plus, it will be the conjugate acid. Okay, now let's write the definition of the K. What's the K? Okay, K is equal to equilibrium concentration of equilibrium concentration of the product divided by the reactant. And those are the product. Okay. So we need to have equilibrium concentration of product, and we divide them by equilibrium concentration of the reactant. Okay. And we do not include any compound that has a state of L or S inside the equilibrium expression. Okay. Water comes with L as a state or liquid, HA, it will be aqueous. This one, it will be aqueous, and hydrogen ion, it will be aqueous. How do I know it? They will tell you that one, okay? And water, because the concentration for it is too high, we're going to say whatever we would lose from it is nothing. So we assume the change with concentration of water, because it's a pure liquid, it will be nothing. So we don't write it. And as you see, this one is gone. And just simply, I say K is equal to product over reactant. Okay, what's the meaning of Ka, Kb, or Kw? So if you have a reaction like HA, acid, reacting with water, liquid, you get equilibrium, and you get A minus plus H3O plus. Okay, this reaction is acidic. Okay, so it's the acidic equilibrium. Okay, I go K. Okay, K what? K equilibrium constant. This is equal to, okay, in order just to call it K, we're going to call it Ka. That means it's acidic. Okay, it's going to be equal to concentration of product to the power of M. If you have more than one, you write it. Okay, divide by concentration of the reactant under equilibrium condition. Okay, what do I have? I have A minus to the first multiply hydrogen ion to the first, divide by concentration of HA to the first. Okay. If your reaction is basic, in that case, you will say Kb. Okay, so say we have this chemical reaction, and we get NH4 plus OH. So K, which is equal to Kb, is going to be equal to concentration of product, NH4, the first, OH to the first, and you take this and you divide by concentration of the reactant, which is NH3 to the first. Okay. So Kw, it will be equilibrium constant for reaction of water, two water molecules, and the Kw, okay, it will be this, H2O liquid plus H2O liquid, you get hydrogen ion plus OH, and K or Kw is going to be equal to concentration of hydrogen ion multiply concentration of OH. Okay. Now, if Ka bigger than 1, that means the reaction wants to go to the product side, and the majority of the mixture is going to be the mixture is going to be a product. Okay. And if Ka is smaller than 1, that means the reaction wants to stay like a majority of the mixture is going to be reactant, and the reaction wants to stay as it is and doesn't want to move. Okay. Now, okay, as you see, it says K, it can be between 10 to the power of minus 15 to 10 to the power of 10. And if Ka, okay, if Ka again is way bigger than 1, that means you're dealing with reaction that's favored the product. Okay. Now, in organic chemistry, we use this term a lot, pKa. Okay, instead of saying Ka or Kb, we just simply stick with pKa to predict whether the reaction is going to move forward or not. Okay, so from now we're going to say that's okay. Ka, okay, Ka is, like you say, you have two Kas. One Ka is 1.3 multiplied 10 to the power of minus 5, and another Ka, okay, and I'm going to say K prime, this is going to be 1.5 multiplied 10 to the power of minus 6. Which acid is stronger? Okay, which acid is stronger, 1 or 2? I'm going to say the one that has bigger Ka is a stronger acid. So 1 is stronger than 2. Okay, 1 is a stronger acid than 2. Okay, but in organic chemistry, we use this term. Again, pKa, and what's a pKa? Minus log of Ka. Okay, so if you have this two, say pKa 1 is, for example, is equal to 4, and pKa for another acid, this one happened to be 9. Okay, which acid is a stronger acid? The answer is going to be, again, 1 is a stronger acid than 2. Okay, because it has a smaller pKa. So it will be opposite, okay, opposite of the pKa. The one that has a bigger pKa means is a weaker acid. Okay, and whenever we run a chemical reaction, the reaction wants to form a weaker acid. Reaction wants to form a weaker acid. And so keep this one in your mind. Okay, so I have a bunch of acid here, and they gave you pKa's. And if you look to the pKa's, the one that has the smallest pKa, it will be the strongest acid. So what's the strongest acid? Number 1, this is going to be the stronger acid, as you see. And the weakest acid between them will be the one that has a pKa equal to 50. So this is going to be the weakest acid. And if the gap between them is 1 unit, that means the acid is 10 times stronger than the second one. Okay. Stronger acid will create a weaker conjugate base. Stronger acid will create a weaker conjugate base. Keep this one also in your mind. Okay, so we have a base, okay, tertiary butoxide reacting with water, and it's generating alcohol plus OH. Okay, the question is going to be this: is this reaction is going to move forward or not? Okay, look to the arrows. Okay, they showed you like you have equilibrium, but one of them is bigger than the second. What does it mean? It means the product, the reaction wants to move to the product side. So this reaction is favored, and it doesn't want to go back. Why? Okay, it doesn't want to go back. Still, you have equilibrium. Look to the pKa. If pKa of the conjugate acid, okay, bigger than pKa of the starting acid, the reaction is going to move forward. Okay, how do I know whether I have 100% conversion or let's say an equilibrium or double errors between them? Look to the pKa. Okay, if the pKa is happen to be, I don't know, the gap between them is something higher than 5, I will say there's high chance maybe the reaction is going to move to almost 100% completion. Next one, look, they wrote it as a single arrow. Okay, they wrote it as a single arrow. Okay, and so if I subtract the two pKa's, the gap between them is 34. That's huge difference between them. It's telling me the pKa product, okay, or the conjugate acid is way bigger than the starting compound. What does it mean? It means this one is really weak acid. In fact, this is 1, 2, 3, 4. This is butane. This is not really acid, okay? And that's the reason the pKa for it is like 50. Barely you can call it, acidic, unless you have a strong base, like there, and then that's it can take, H from water or anything in front of it. Okay. What will happen if I don't have a pKa to predict whether the reaction is going to move forward or not? In that case, we'll be dealing with a term that we call it RU. And so RU. And this one is going to be actually our guidance for how to figure whether the reaction is going to move on or not. Thank you very much, and I will see you soon.